In 1993, Japan broke through with the first commercial-scale ultra-supercritical steam turbines. For 30 years, turbines operated at mere supercritical temperatures, limited by the properties of the steel they were produced from. It took nearly 2 years of R&D for Japan to develop the technologies to bring that steel to the market. In today's video, we explore a coal-centric technology, the 30-year march from supercritical to ultra-supercritical steam turbines. Power-generating steam turbines are a technology well over 100 years old. Inside a thermal power plant, an energy center heats up water in a boiler. This energy center can be coal, oil, nuclear, or geothermal. Most of the time, it is coal. The heated water turns into steam. That steam then hits the turbine blades and violently expands, producing mechanical energy that spins a generator and creates electricity. The steam, now cooler and under less pressure, is then returned to the boiler, where it is condensed back into a liquid state. This is the rankine cycle. Thermal plants are not as efficient as a hydroelectric plant, which can get to as high as 90%, as compared to a thermal plant's 30 to 60%. But thermal plants are cheaper, smaller, and less location-specific. We define a steam turbine's efficiency as how much of the fuel's heating input is turned into usable electricity. Like all heat engines, steam turbines have a maximum efficiency, the Carnot heat engine efficiency, the difference between the energy levels of the steam entering and leaving the turbine. The steam's energy level leaving the turbine tends to be fixed, as it is tied to the turbine's environment. So the most practical thing to do is raise the other side of the equation, the energy of the steam going into the turbine. So over the past 70 years, that has been the general summary of the steam turbine's technical evolution, getting the steam hotter and putting it under higher pressure to make it more energetic. There was an interesting efficiency side quest involving reheat cycles. After the steam expands in a high-pressure turbine, it is sent back to the boiler for reheating. The reheated but lower-pressure steam then hits a second intermediate turbine and maybe even a third lower-pressure turbine. Only after that is the steam finally condensed back to a liquid. Reheat cycles both add thermal efficiency and protect the turbine blades by reducing the steam's moisture content, though they do add considerable complexity to the turbine design. Anyway, the more efficient the turbine is, the less coal or oil we need to burn to get the same number of megawatts, which is a big deal because fuel is the dominant factor in the cost of electricity. One additional percentage point of efficiency can save millions of tons of coal from burning each year, reducing carbon dioxide emission by about 2 to 3%. A major efficiency problem that soon emerged, however, was boiling. Imagine a pot of water on the stove at sea level. You add heat to the pot until the water reaches its boiling temperature of 100 degrees Celsius, and right on cue the water starts to boil. Now, suddenly you find that adding more heat no longer increases the temperature. More heat energy only produces more bubbles. It does not give you hotter steam, which is what you need to further raise the turbine's efficiency. But if the water's pressure and heat go beyond a certain critical point, 22.1 megapascals and 374 degrees Celsius, well, then something weird happens. The water becomes a dense fog-like thing that we call supercritical fluid, bestowed with the properties of both gas and liquids. It effectively becomes steam without boiling. We can now raise input steam temperatures with more heat energy, achieving ever better efficiencies. Going supercritical also made these boilers somewhat safer. Older subcritical boilers had something called a steam drum. After water is boiled into steam, the drum separates the steam. Going supercritical means we no longer need the steam drum. Removing it not only reduces the system's weight, but also improves safety because the drums being full of hot, highly pressurized fluid posed explosion risks, as many a train has discovered. We call such designs once-through boilers, first patented by the engineer Mark Benson in the 1920s. Because water passes through the heating system only once, it goes into the boiler cold and leaves as supercritical steam. And yes, we probably shouldn't call supercritical boilers anymore, since they are not actually boiling, but inertia is a powerful thing. In the 1950s, the American Electric Power Company joined with turbine maker General Electric and boiler maker Babcock and Wilcox Company to build the first commercial supercritical power generation unit, Philo Unit 6. With a max capacity of 125 megawatts, Unit 6's feed water was pressurized at 37.9 megapascals. Prior to this, no steam power plant had reached 22.1 megapascals. The steam's main operating temperature reached 621 degrees Celsius, 28 degrees higher than what had been previously possible. At these temperatures, the steel pipes literally glow red. The unit's thermal efficiencies touched 40%, also a clear cut above anything else then available. After Philo Unit 6, a second supercritical power generation unit fired up in 1961, Eddystone Unit 1. Built by the Philadelphia Electric Company, Eddystone steam reached operating temperatures of 649 degrees Celsius and pressures of 34 megapascals. The Soviets also got into the fun, launching a prototype turbine called the SKR-100 in 1968. It achieved steam conditions of 30 megapascals and 650 degrees Celsius. But Unit 6 led the way. A manager for mechanical engineering at the successor company, AEP, would later say about it, "For its day, Philo 6 was like flying to the moon without taking the intermediate steps of first orbiting the Earth and then sending up an unmanned spaceship." But perhaps, as the metaphor implies, it soon became clear that Unit 6 and its early peers had taken a step too far. Such intense heat and pressures were not sustainable. The reason had to do with the steels. Steam turbines share a few common steel components. The casings and shells are big pieces of steel that offer structural support and hold in steam. Being so big, their steels cannot be too expensive. Bolts hold things together. These have to be highly resistant to stress and might find themselves exposed to very high temperatures. The blades spin around. They experience the steam gas directly, but are thin and cooled by the flow. So it is the turbine rotor, the part that spins the blades, that experiences the hottest temperatures. The rotor is thick and solid and receives heat conducted into it from the blades. It is one of the biggest challenge areas from a metallurgical perspective. Turbines and boilers are made from a limited range of steels to ensure good match of thermal properties. Supercritical units in the day use largely two types of steel. For most components, they use 2.25 Cr1-Mo steel, or T22 steel. The name refers to its components of chromium and molybdenum. The high chromium content makes T22 part of a class of steels known as ferritic steels. They're called that because they have a body-centric cubic crystalline structure. T22 is a good steel that welds easily and offers good creep strength. Creep meaning a tendency for the steel to deform after long periods of high temperatures and strong mechanical forces. Creep is a very serious problem for both steel and people alike. But above 560 degrees Celsius, T22 starts to lose that creep strength. So the hottest parts of the turbine, like the rotors, were made from what are called austenitic steels. These steels have a face-centered cubic crystalline structure. Austenitic steels contain high amounts of nickel and chromium and are very temperature resistant. They are a bit expensive thanks to that high nickel content, but there were two other more serious problems. First, these austenitic steels expand a lot in high heat while also poorly transferring that heat. So when the turbines start up and shut down, their thick-walled components will have hotter outsides but cooler insides. The hotter areas expand more than the cooler inner areas, thus leading to cracking. Second was oxidation. Superheated steam can oxidize the steel, creating oxides on its surface that eventually flake off. These flakes then either build up in the boiler tubes, blocking their flows, or chip away at the turbine's insides, breaking them. These were complicated problems. Therefore, subsequent turbines ramped down to 23.8 megapascals and main steam temperatures between 541 and 566 degrees Celsius. This neighborhood is generally classified as supercritical. The old neighborhood, anything over 25 megapascals and 593 degrees Celsius, formed a new category called ultra-supercritical, though I must admit that the borders between the categories are quite fuzzy. Various sources have their own numbers. Great work was needed to get to ultra-supercritical categories, but with coal being so cheap at the time, there was little economic incentive in the U.S. for this efficiency gain. The vast majority of America's thermal plants remained subcritical. By the 1960s and 1970s, just 15% were supercritical class. So, for 20 or so years, the operating temperatures and pressures of the world's top coal-fired power plants remained steady. Instead, American utilities focused on scaling turbine size and capacity to 600 to 1,000 megawatts. Even this hit some limits at the end of the decade. The insane physics and tolerances on metals inside such a huge turbine caused unexpected maintenance and extended downtime costs. In the 1950s and 1960s, Japanese companies gained technical proficiency through technology transfers with the West. By the 1970s, Japanese oil-fired thermal plants operated steam of 16.6 megapascals and 566 degrees Celsius, short of supercritical conditions, but good enough for 35% thermal efficiency, on par with similar plants in the United States and Europe. Then came the oil crises of the 1970s. High oil costs, plus an international ban on new oil-fired thermal plants, forced a transition to a diverse energy portfolio of imported coal, LNG, and nuclear. Thusly, the government funded a rapid transition to supercritical class turbines, the first of which were two 500-megawatt units in Matsushima power plant. The Japanese government then embarked on an R&D project to make ultra-supercritical power generation a reality, seeing them as enabling coal diversification while also meeting internal carbon emissions goals. After feasibility studies in 1979, the research program at the Wakamatsu Institute began in 1982. As I said, the ultimate issue was if the turbine steels can sustain the high thermal and mechanical stresses over long periods of time. It would take over 10 years to develop the metals for this. Phase 1 of the project spanned until 1994 and was split into two steps, which I shall call 1A and 1B. Phase 1A studied older ferritic steels to achieve conditions of 31.4 megapascals and 595 degrees Celsius. Meanwhile, Phase 1B looked at austenitic steels with the hope of achieving 34.3 megapascals and 650 degrees Celsius, with 595 degrees in the intermediate and lower pressure reheat cycles. There was great hope in this initially, but in the end the austenitic steels failed to work. Though blends were found that can sustain those temperatures, tests concluded that the thermal expansion coefficient still caused them to eventually warp and break. After building test turbines at Wakamatsu, Mitsubishi Heavy Industries leveraged the Phase 1A learnings to build the first commercial-scale ultra-supercritical turbine in the world, the 700-megawatt Hekinan Unit 3. Unit 3 operated at temperatures of 593 degrees Celsius. It first fired up in April 1993, marking a long-awaited return to ultra-supercritical conditions. Meanwhile, in Phase 2, the Japanese program, which was a joint venture between Wakamatsu, Mitsubishi, and the Japanese steel company Kobelco, discovered a line of advanced 12CR ferritic steels. There are 4 of these steels, but the most well-covered one is Mitsubishi's TMK1 steel. I am in awe of this steel. I don't know how many people care, but this is some special steel. TMK1 descends from a 12% chromium steel originally made in England by William Jessup and Sons for jet engine discs, called Meltrol H46, produced with a proprietary blend of 9 element additives from carbon to boron to vanadium to tungsten. H46 had good creep strength. General Electric took this steel and in 1965 reduced the proportion of niobium. This produced a line of 12% chromium steels sometimes used for rotors during the supercritical 566 degrees Celsius era. They called it 12CR MOVNB. To create TMK1, the Japanese simply had to do one thing: tune the amount of molybdenum in relation to how much tungsten was in the steel. This was done thanks to experiments on H46 done by Professor Fujita in the 1970s. Fujita discovered that raising molybdenum content from 1% to 1.5% helped hold together the steel's internal structure and keep it from creeping. Too much molybdenum, however, would cause the steel to create delta ferrite structures that undermine that long-term creep strength. So 1.5% precisely. No more, no less. Fujita's steel, called TAF, was not suitable for large items like rotors, so Mitsubishi and Kobelco worked together to scale up the methods to produce larger steel items. Producing this steel requires some insane skills. The raw steel mix is first melted using electricity in a vacuum, which removes hydrogen and nitrogen gas impurities. The output is then cast into a solid intermediate product. This metal is then carefully remelted by turning it into an electrode and passing AC electric current through it, a method known as electroslag remelting. The metal melts drop by drop so it can be cast into the cleanest, most uniform ingot possible. The massive ingot is then forged into shape while it is still hot. Then finally, the metal is heated, cooled, and reheated 4 times at temperatures of 700 to 1100 degrees Celsius. These heat treatments are to create and lock in the steel crystal microstructures necessary for the steel to survive insanely high temperatures, pressures, and mechanical forces without fail for over 100,000 hours. Mitsubishi Heavy Industries used TMK1 for the rotors of the Matsuura thermal power plant in Unit 2. It began operations in 1997. At 1,000 megawatts, it was the first large-scale ultra-supercritical steam plant. With operating steam pressures of 24.1 megapascals and temperatures of 593 degrees Celsius, its thermal efficiency of about 42% broke new ground. Recall that supercritical plants had about 34 to 35% efficiency. Matsuura's success kicked off a new turbine boom in Japan. Better steel recipes came out with improved heat and creep resistance. And by 2001, there were 13 ultra-supercritical power generating units online in Japan. By 2013, 25 units. This includes some of the most efficient coal-fired power plants in the world, a notable one being the Isogo Thermal Power Plant Unit 2, a 600-megawatt ultra-supercritical turbine. Produced by Hitachi, the turbine operates at a wonderful 25 megapascals and 600 degrees Celsius. Notably, it adds 1 reheat cycle, raising the temperature to 620 degrees. The thermal efficiency was a record-breaking 45%. It is worth noting that the European community has also spent efforts to develop ultra-supercritical thermal plants. The core of the European effort was a program called AD700. Begun in 1988, it has sought to produce a demonstration plant with steam operating at 34 megapascals and the neighborhood of 700 degrees Celsius, maybe even 750 degrees. which is basically basaltic lava flow range. Such a system would have thermal efficiencies of 50%. They dubbed this category Advanced Ultra-Supercritical. The limits of ferritic steels and others are around 620 degrees Celsius, so the focus has shifted to nickel-based superalloys. Their production requires even more demanding melting processes and heat treatments. However, by the 2000s, the European community had started a shift towards renewables. The AD700 demonstration plant was eventually built in 2005, Comtes 700 in Germany, which operated for about 4 years. But continued work on 50% efficient coal-fired thermal plants has been de-emphasized. These technologies have since moved over to Asia. Japan remains a technology pioneer, but they are increasingly adopting LNG. So these thermal plants are most thriving in India and the People's Republic of China, countries that still heavily rely on coal. Coal-fired thermal plants occupy a funny place in the portfolio. The steam turbine is the OG turbine, but there are others out there. A notable one is the gas turbine, which directly takes in natural gas or refined fuels to produce electricity. Lots of overlap with jet engines. There are even versions where the heat in a gas turbine's exhaust is captured to power a steam turbine a la human centipede, a combined cycle gas turbine or CCGT. Measured on point-to-point efficiency, CCGTs beat standalone steam turbines at about 55 to 60% for the former compared to 42 to 45% for the latter. And since they cook with gas directly, you skip a big boiler, though you still need to produce steam. But nothing quite beats coal versatility, storability, and low sticker price. Yeah, CCGTs are more efficient, but dead cheap and plentiful coal beats more expensive LNG, carbon pricing not included. Moreover, these steam turbines are huge. Gas turbines generate anywhere between 100 and 400 megawatts of power. Modern steam turbines can get to a staggering 1,500 megawatts, operating for weeks or months on end to provide steady baseload power to the grid. Despite the rise in world renewables capacity, coal remains a dominant power source, and I struggle to see a path away from it entirely, despite the carbon footprint. So producing more electricity from less coal should be a key goal in the future. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.